Hi, my name is Greg. Last time I talked to you quite a lot about moles and kind of how they're all to do with, well, the Avogadro constant. And, well, you can think about that and say, well, if it's a constant named after Avogadro, there's probably a guy called Avogadro. And there was. His name was Amedeo Avogadro. And he was quite an amazing guy, really. He was a lawyer, a physicist, a mathematician, a chemist, and really, he didn't even try to be a chemist. He just came up with a lot of useful stuff in terms of chemistry using physics, and he spoke a bunch of different languages. And what did he really come up with? Well, he came up with what we now call Avogadro's law. So if you look at a couple of different solids, right? So for example, here I've got 1 mole. Well, ethanol is not really a solid, but ethanol is a liquid. But if I just compare the liquid ethanol to solid sulfur and solid iron, as you can see, 1 mole of ethanol and 1 mole of sulfur and 1 mole of iron. I know they're just rough diagrams, but I just wanted to show you that they can take up different volumes in space, and that's really important. So what we often use to talk about this kind of stuff is density. So the equation for density, which is either written as D, is mass over volume, or sometimes it's written with the Greek letter rho, so rho equals mass over volume. So what units are we going to get? Let's think about it. Well, mass comes either in terms of grams, kilograms, milligrams, or tons, or stuff like that. Volume comes in terms of stuff like centimeters cubed, decimeters cubed, and meters cubed. In terms of solids, we tend to use mass in terms of either kilograms or grams. I'm going to use grams here. And we tend to use the volume of solids as centimeters cubed. So the unit that we're going to get is grams per centimeter cubed. And as an example, the density of copper is 8.96 grams per centimeter cubed. So that's the density of copper. Okay? Now, this works all nice and fine for our solids and our liquid ethanol here. But really, we had to do this at some sort of certain condition, right? So when you think about it, if I increase the temperature, right, and I know I'm not going to be able to explain it very well here without explaining some parts of atomic structure and kind of how atoms bond together, but when you increase the structure, you can imagine the molecules move apart a bit, and really what ends up happening because of that is simply the volume increases, and the pressure can also affect how much volume something takes up. So when you're measuring density, you've got to assume, or use rather, not assume, use the same temperature and pressure for each and everything you're measuring. Now, there's lots of different things you can use. There's standard state, standard conditions, normal temperature and pressure, and they all give slightly different values. So some of them use temperature of, for example, 0 degrees Celsius. Some of them can use a temperature of 25 degrees Celsius. Some of them use a pressure of 100 kilopascals. Some of them use a pressure of 101.325 pascals. Kilopascals. So there's quite a lot of different values you can use, really, and that's why I'm not going to quote one specific value. I suggest that you look up the one that maybe you're using in something like chemistry class for now. But let's build on this idea in terms of gases, right? So for a gas, yeah, we can still use the same temperature and the same we can still use the same temperature, and we can still use the same pressure when measuring gases, but something rather interesting pops up with gases. You see, with gases, it's not that great to be working with in terms of grams, so let's work with moles instead, right? Now, how can we do that? Well, this is all to do with Avogadro, actually, and this is the equation that's going to make this so crucial. The number of moles, N, is equal to the volume of something divided by its molar mass, or if you want to measure the molar mass of something, that is equal to the number of the volume divided by the number of moles, right? Now, what really is molar volume? Molar volume is simply you can think of it as the kind of the volume that a certain number of moles of something takes up, right? Let's try and figure out the units of molar volume. The units of molar volume are generally grams, decimeters cubed per mole, right? Now that's a bit of a weird one to figure out. So how can we figure it out first of all, right? Well, there's a nice way to link density, which is what I just showed you, that mass over volume, into molar volume. So the way that you can kind of derive molar volume first of all is to use the property that molar volume is equal to an MR of a substance divided by the divided by the density of a substance. Now, when you think about it, the MR comes in terms of grams per mole, and the density comes in terms of grams per centimeter cubed, right? But the molar volume tends to come in decimeters cubed, decimeters cubed. So we can just change our density to decimeters cubed, especially since I'm not playing with anything too specific here. Let's just make that a bit clearer there. Okay, decimeters cubed, grams per decimeters cubed. So let's think, if I've got grams on top and grams on the bottom, that's going to cancel out. Now I've got per mole on top, that's going to stay as per mole. However, because I've got per decimeter cubed on the bottom, the -3 actually becomes a +3, so I'm just left with decimeters cubed. So I can figure out that the units of molar volume are actually decimeters cubed per mole. Kind of difficult to fit it in there. I'm going to try a bit better. Maybe above it. Decimeters cubed per mole. Okay? And the second way you could figure it out is use the equation that V over N equals the molar volume. So a volume we know comes in terms of, in the example of solids, we said it comes in centimeters cubed, but in the example of gases, it has to come in decimeters cubed instead. So we've got decimeters cubed on top. Maybe I'm going to use a different color for this. Let's just change that. So this comes in terms of decimeters cubed. And moles come in, well, moles. So you've got decimeters cubed per mole. So that's the second way you could figure it out, that the units of molar volume have to be decimeters cubed per mole, right? Or decimeters cubed are really the same as liters, so you could say liters per mole if you prefer that, but I think decimeters is a bit nicer. So really, what's the deal here? What's the deal with molar volume? Well, with gases, there's a very nice property of molar volume. If you were to think about molar volume for copper and for different solids and liquids, there's nothing too special about it. But for gases, you might have noticed that I've listed some gases. I've got hydrogen gas, I've got methane, I've got oxygen gas, I've got hydrogen chloride, hydrogen iodide, and xenon. So I've got 6 different gases listed. Then I've listed out their MR and their densities, right? And obviously the units grams per mole and grams per decimeter cubed. I then plugged these values into that Vm equals mR over d equation. So molar volume equals relative, well, I'm not going to call it relative molecular mass, although I'd rather call it molar mass, divided by the density, right? And what that gave me is that for most gases, the molar volume is actually 22.4, ranging slightly down to 22.1 for hydrogen iodide and 22.3 for hydrogen chloride, but it's very close. And this is what Avogadro's law is all about. This is what Avogadro discovered. Avogadro discovered, I've actually got it written down here, that equal amounts of different gases at the same pressure and temperature take up the same volume, no matter how many atoms make up a molecule. So I could have a molecule, such as CH4, which is made of 4 atoms, and I could have a molecule like O2, made of 2 atoms. I could have a molecule like xenon, made of just 1 atom. And if the amount, by which I generally mean either moles or mass, right? Let's stick with moles. If I've got the same number of moles of these, and I apply the same pressure and temperature, they will take up the same volume. And that is Avogadro's law. Next time, I'm going to show you some possible calculations you can do with Avogadro's law and the equations I showed you today.